All right, folks, let's go ahead and let's pick up where we left off with yesterday. Let me go ahead and start the timer here. And what I would like to be able to do today is to kind of to wrap things up. I really want to be able to make the connection. I want you to be able to make the connection between the geometry of a molecule and the hybridization. We learned about hybridization before we got off on break, and that was quite a difficult. I think it was a difficult topic for many of us to kind of wrap our minds around. And one of the things that was very difficult was then how then do we determine the hybridization of a given atom when it's part of a molecule? How do we know that it's sp? How do we know that it's sp2? How are we supposed to know that it's sp3? We were able to talk about a little bit about how, depending on what type of bond we have, if it's a single bond, double bond, or triple bond, from that we can determine whether we have sp2, or sp3 hybridization. But that was still a little bit difficult to understand because how do you visualize, how are you supposed to be able to understand what the bond is? Now we can draw it on paper, obviously, that's what the Lewis dot structures are. But what the geometry of these molecules give us is real data about how these atoms are situated in space, but also it confirms for us the hybridization. And that's what I want to be able to work through with you today. I want to be able to talk about the geometry, finish up talking about that, and that's where I want to start out with you here on the screen here. I want to talk to you about that. Then I want to talk about then how we can use that information about the geometry to complete our characterization of a molecule. And so we're going to practice that today. And we're going to hopefully by the end of the lesson today, if I give you a molecule, you should be able to characterize it in the ways that we're going to talk about today. Okay. All right. So let's pick up where we left off with yesterday, and that is we talked about electron geometry and we talked about molecular geometry. Now remember, with electron geometry, and please make sure you make use of the PhET lab to help you with this. Okay? When we talk about electron geometry, we are taking into consideration the way that all of the electron domains are situating themselves around an atom. Okay, so when we talk about electron geometry, we're talking about the location of all of the electron domains, both bonding and non-bonding domains. Okay, so make sure you keep that in mind. When we talk about the molecular geometry, we are only considering the bonding domains. How do the bonding domains situate themselves around the atom relative to one another? Okay, so that's the key difference between electron domain and the bonding domain. What you need to make sure you keep in mind then is that when we talk about the hybridization of an atom, we need to take a look at the electron domain. We need to consider then all of the electrons, all the electron domains that situate themselves around the atom. Okay. All right. So with that said, then yesterday I was able to point out to you, and I'm going to emphasize this again. You need to be able to make sure then that you can memorize all of the geometries above that red line. Okay, so we have then six different or not six different, but we have six geometries that you need to make sure you remember. We have the linear, trigonal planar, tetrahedral, bent, trigonal, pyramidal, and then another bent here based upon the tetrahedral electron geometry. Okay, so we have then electron geometry versus molecular geometry. Make sure you are able to identify then and remember the six, and I'm going to highlight them here for you, six different geometries that you will be asked to answer questions about when you take the exam on this chapter. Okay. All right, so let's go ahead then, and I'm going to go ahead and save this for you because this is what you'll need to know and make sure that you are familiar with these six different geometries here. Okay, so how do we relate then? And this is what I want to finish up with here. How do we relate then the electron geometry here to the hybridization of a particular atom? Okay, all right. So if we take a look at the electron geometry here, we have two electron domains. Now here, this could be two bonding domains. It could be a one bonding and one non-bonding domain. But the idea then is that with this electron geometry, we have two electron domains. Okay, so just to the side here, this is what we talked about in one of the periods. Okay, so what we have here then is when we have electron domain in which you have two electron domains. Okay. When you have two electron domains, what we can be certain of then is that the hybridization that allows that the allowed two electron domains in is going to be then the sp hybridization. Okay, so this is going to be sp hybridization that can account for then the two electron domains that situate themselves around a central atom. Okay. All right, so if we take a look at this end, we have then a situation in which we have three electron domains. So when we have three electron domains, okay, we then have an atom that is hybridized to the sp2 hybridization. Okay, that is subject to sp2 hybridization, and that's what we know about that. So remember, these are electron domains here, not bonding, not just simply bonding domains, but both bonding and non-bonding. We got to take into consideration both of those. So we were talking about electron domains here. Okay. All right. Finally, then we have a situation in which we have 4 electron domains here. So we have 4 electron domains, and whenever we have a situation in which we have 4 electron domains, and that's what we see here. Okay. The hybridization that can account for that, the hybridization that will give rise to that, then is going to be sp3 hybridization. Okay. And so that's how we can use then the geometry, the electron geometry of an atom in order to determine then its hybridization. So you got to make sure you keep that in mind as you move forward with this process here, where we characterize a particular molecule. Okay. All right. So look for the bond angles. Okay, so what you want to make sure you do, and let me go ahead and save this here. So you want to look at the bond angles to help you determine then the electron geometry, but also use the bond angles to help you with the help you with the geometries, the electron geometry as well, because it's going to be the electron geometry which takes into account the electron domains that we will look for to determine then the hybridization. Okay. All right. Very good. Let me go ahead then and let's take a look at some examples. Let's take a look at some examples here where you will be asked then to consider the hybridization. Okay. Oops. Okay. Well, let me go ahead. Yeah. All right. So when we talk about VSEPR theory, let me make sure I review this with you. We're talking about then the shapes of a molecule based upon how the electron domains, electron pairs, repel one another, and that's the essence of VSEPR theory. And if depending on how many of the electron pairs we have, we're going to have then different ways they will configure themselves around the center atom. Okay, so let's make sure then keep that in mind. So let's take a look at some examples here, and let's take a look at these 4 molecules here. Okay. So we have methane here, and let me just quickly review this for you. What you're going to notice is in each one of these molecules here, there's going to be 4 electron domains. Okay, so let's make sure we count that. So I refer to it as 4 electron pairs here in this slide here, but if you take a look at this, in each one of these molecules here, what they all have in common, what they have in common, what they have in common then is that they have 4 electron pairs as bonds or lone pairs. Essentially, what we have then is we have 4 electron domains around all these. Okay, so we have 4 electron domains. So what this is telling us then is in each one of these molecules, then we have 4 electron domains. Immediately, as soon as you see that, folks, you should recognize, or hopefully at some point, you should be able to recognize that when you have 4 electron domains around a center atom, okay, what can we conclude about that? Whoops, come on, where are we? What can we conclude about that? That each one of these atoms, and each one of the center atoms here, the black one, the brown, blue, the red, and the green, that all of these will be sp3 hybridized. So that's what we know. As soon as we identify them, that each one of these here have 4 electron domains, the conclusion we can reach is that the hybridization for each one of those center atoms is going to be sp3 hybridized. Okay, so you got to be able to recognize that as you move forward with this. Okay? And so therefore, each one of these will have a tetrahedral electron geometry. And again, the terminology here is a little bit different than what I've used here. Okay, so what we have then is each one of these then, the electron geometry is going to be tetrahedral. Okay, so the tetrahedral shape here refers to then the electron geometry. And so again, if you want to use that to help you as well, whenever you have a tetrahedral electron geometry, you know then that the hybridization will be, again, sp3. So both of those, the fact that we have 4 electron domains, the fact that the electron geometry is tetrahedral, we can use that to help us then to deduce or to determine then that the hybridization of each one of these atoms will be sp3. So therefore, the carbon atom here in methane, this center carbon atom then is going to be sp3 hybridized. And so we talked about this already in a couple of the periods already. But that also holds true for the nitrogen here, in the center atom for ammonia. That will also be sp3 hybridized. The oxygen atom here will also be sp3 hybridized, as well as the fluorine atom here. All of these atoms here will be sp3 hybridized. Why? Because each one of these here have 4 electron domains, and that the electron geometry, the shape in which the 4 electron domains take around the center atom, will be tetrahedral. Okay? So that's how we know then that each one of those atoms will be sp3. Okay? All right. Let's go ahead then and let's characterize each one of these atoms. Let me go and save this really quickly. Okay. I'm sorry, you characterize each one of these molecules. Now that we have determined then each one of these, the hybridization of each one of these, okay, it becomes easier to characterize these atoms. Okay? So how do we go about characterizing these atoms? When we go about characterizing these atoms, there are at least 6 things, and I'm just asking for 6 things that we want to make sure we indicate when we characterize these atoms here. And what are the 6? Okay. Right, first, you need to be able to describe then draw then the Lewis dot structure. You need that, the Lewis dot structure first. Okay. Now here I give you actually not only the Lewis dot structure, but I give you the 3-dimensional structure as well. This is the structure, both the electron, the 3-dimensional structure as well. But make sure then that if what I do is what you'll see then is if I give you the formula, for example, the formula for methane is CH4, the formula for ammonia is NH3, the formula for water is H2O, and the formula for hydrogen fluoride is HF. If I give you just the formula, you should be able to draw the Lewis dot structure. Why? Because you need to use that Lewis dot structure to determine then the different electron domains. Okay, you got to be able to indicate the electron domains. I'm sorry, let me go ahead. A little bit neater. Let me go this really quickly. But you have to be able to indicate the electron domains for each one of these molecules as well. So let me go ahead. Let me write this a little bit more clearly for you. Okay. So indicate the electron domains. Okay. Which includes then the bonding and non-bonding pairs. Okay. Bonding and non-bonding pairs. And remember, electron domains, when it comes to electron domains, we treat single bonds, double bonds, and triple bonds all as a single, a type of electron domain. Okay? They don't represent anything different. Okay? All right, so you want to be able to characterize the molecule by its electron domain. Okay, then you want to also be able to describe the bonding interactions. Sorry, bonding interactions. And remember, these bonding interactions are how the orbitals overlap with one another. And there are 2 ways that we can describe that. We can describe it as a sigma bonding interaction and also the pi bonding interaction as well. Okay. All right. Next, you want to be able to determine then the electron geometry. you want to be able to describe the electron geometry and and the molecular geometry. So you got to be able to do both of those as well. And then finally, you want to be able to describe then, oops, I'm going to try to fit in there, the hybridization. Okay. And this will give a very complete description, for the most part, a complete description of the molecule itself. So if you can describe a molecule in these 6 ways here, you will give a very thorough description of the molecule. Okay, so let's go ahead then and let's practice this with these 4 molecules here. Okay. All right, let me go ahead then and let's go ahead and characterize the first one. Let's characterize methane. Okay, let's go ahead and do that first. Okay. All right, so methane. Again, you have the Lewis dot structure here, but really, if you had to draw the Lewis dot, I give you the 3-dimensional structure here. The Lewis dot structure for methane then would be this, where you have carbon surrounded by the 4 hydrogens. So that would be then the Lewis dot structure for methane. Okay, so hopefully you should be able to do that. Remember, with the Lewis dot structure, what you want to make sure you do then is every atom, for the most part, must follow the octet rule. There are some exceptions. The only atoms that will not violate the octet rule, for the most part, would be carbon, nitrogen, oxygen, and the halogens. And most of the time, you'll see the halogens adhere to the octet rule. So those atoms must always obtain their octet. The other atoms can violate it by either having more or less. So make sure you review all that in order to be able to write out the Lewis dot structure for these molecules here. Okay. All right, so with that said, then let's take a look at the electron domains. Okay, so let's so that's the very first thing you want to do. Okay, so the electron domains here, if you take a look at this, we have then 4. If we consider this, we have 4 bonding domains. We have 4 bonding domains. Okay, because all 4 of the electron pairs there are bonding electron pairs. And furthermore, these bonding domains here are all single bonds, and we can write that in as well. Okay, so each one of these bonds here are single bonds, and each one of the single bonds count as a single bonding domain. Okay, all right. So with that said, then once we have that, okay, the bonding interactions that we have here, then we already saw this. Then it's going to be an overlap, that is a side-by-side overlap between an sp3 and an s, and so therefore a bonding interaction here is going to be a sigma bonding interaction. We don't even need sigma bonding interaction. Really, we can determine this based simply on the fact that we have all 4 single bonds. Remember, when it comes to sigma bonding interaction, whenever you have a single bond, that will be a sigma bonding interaction. So again, we don't need to know the hybridization in order to get to that point. Okay. All right, let's go ahead then, and this is all for methane now. Okay. Let's take a look at the electron geometry. We have 4 bonding domains. And so therefore the electron geometry is going to be a tetrahedral bonding electron geometry. Okay, and because all 4 of these domains are bonding domains as well, the molecular geometry will also be tetrahedral. Now remember, the difference between these two then is that with the electron geometry, we take into account all of the domains. With the molecular geometry, we only consider then the bonding domains. And so for methane, then, since we have all 4 bonding domains, in both cases, then the geometry will be tetrahedral for electron geometry and for molecular geometry. All right. Finally, hybridization. With that said, then we saw then that if you have a tetrahedral electron geometry and we have 4 bonding domains, and we have 4 domains here, 4 electron domains, and all electron domains happen to be bonding, but we have 4 electron domains. That means then that the center atom is going to be sp3. Okay, so carbon's going to be sp3 for carbon, and we can go ahead then and characterize the hybridization for hydrogen as well, and that is unhybridized. It's an s orbital for hydrogen. Okay. All right. So that's it. That's how we go about characterizing um, the methane molecule, okay, based upon what we know about bonding, about hybridization, about how these electron pairs repel one another. Okay, so please make sure then that you ask questions if you're not quite sure about this. Okay? All right. With that said, then let's take a look at ammonia. Let's do ammonia together, okay, and then I'm going to ask you to do water in just a moment, and then hydrogen fluoride. Okay. All right. Let's go ahead then and let's do water. Let's do ammonia. Okay, so ammonia then, the Lewis dot structure for ammonia, we can start out with that. It's going to be nitrogen, center atom, single bonded to hydrogen. And again, if you're not quite sure how I'm getting this structure here, please make sure you come by and see me. Okay, and so with that one lone pair there as well. So again, I give you the structure for that. Okay. All right, so in terms of electron domains, then let's take a look at what we have here. We have then 3 bonding domains. Okay, and 1 non-bonding domain. Okay, for a total of 4, and then I'll just write it in parenthetically, 4 electron domains. So we have a total of 4 electron domains, and why do we need that? Because again, if we have 4 electron domains total, we know then the electron geometry, and thus we also know the hybridization. Okay, so that's why I want to write that there for you. Okay, all right, but we have 3 bonding domains, 1 non-bonding domain. The 3 bonding domains are all single bonds, and so make sure you keep that in mind as well. Okay, all right, so let's go ahead then bonding interactions. Okay. Since these are all 3 single bonds, okay, we know then that the bonding interaction is going to be a sigma bonding interaction. Sigma bonding. Okay. Electron geometry. Let's go and deal with that now. Electron geometry is all obviously going to be tetrahedral because we have then 4 electron domains. Okay. The molecular geometry now, because we have 3 bonding domains, and that's what we consider 3 bonding domains in which you have this lone pair right here. We know then that the molecular geometry here is going to be trigonal planar. And so and the way you can identify this is by memorizing the fact then that when you have a molecule with 4 electron domains, and only 3 of them are bonding, then we have a trigonal planar molecular geometry. Okay. All right, finally, with that said then, hybridization should be pretty straightforward based upon the tetrahedral electron geometry and the 4 bonding domains here. We know then that ammonia is going to be then sp3 hybridized. Okay. All right. Let me go ahead and save that for you. I'll ask you to do water in just a moment. Let me go ahead and do one last one for you. Let me go ahead and do hydrogen fluoride for you. Let's take a look at that. Hydrogen fluoride then. Okay. Lewis dot structure for hydrogen fluoride. Okay. It's going to be HF with the lone pairs on fluorine to complete the octet. Okay. All right. So with that said, then we have then in terms of electron domains, we're going to have 4 total electron domains. So 4 total electron domains. Okay. Of those 4, then we have 1 that is bonding. Okay, and 3 that are non-bonding. Okay. All right. So with that said, then let's go ahead and let's take into account the bonding interaction. We only have 1. So the bonding here, domain here is a single bond. And so therefore, as a single bond, it's going to be sigma bonding interaction. Okay. All right. So electron geometry, then we have 4 electron domains total. And so therefore, the electron geometry here is going to be tetrahedral. Okay. And if we only have one bonding domain, the molecular geometry then will be linear. Okay. And then finally, then if we have 4 electron domains, the hybridization is going to be sp3 for the fluorine, and again, it's going to be s orbital, unhybridized s orbital for the hydrogen. Okay. All right. So please make sure then that you practice this. And like I pointed out to you earlier, the book doesn't do quite a sufficient job in giving you some practice with this. So I'm going to be working a few more of these out with you. Okay. And so let's go ahead then and let's start with water. Okay. So I'm going to ask you, so if you need to pause the video to go back and see how I did this, please make sure you do so. But what I would like you to do now then is, let me go ahead then and let me ask you to characterize, okay, water. Okay, so water then, make sure that when you characterize water, take about a couple of minutes to characterize water. When you do so, make sure you indicate then or draw the Lewis dot structure, describe the electron domains, describe the bonding interactions, describe the electron geometry and the molecular geometry, and then finally describe then the hybridization of oxygen in this molecule. Okay, so take about 2 minutes on your paper. Please make sure you indicate that, and then when we come back after you unpause the video, okay, we'll talk about how we can characterize this. Okay, so go ahead, take 2 minutes. Okay, let's go ahead and let's take a look at this, you guys. Let's see how you did. Let's compare your answers to what I give you here. Okay, and then if you have any questions, please, like I said, stick around tomorrow after I dismiss everyone to watch the lesson. Or if you're in school, you can ask about it as well in class because we'll be discussing it. Okay, but please make sure if you're not quite sure how I come up with this description here, please make sure you come by and you get your questions answered. Okay? All right, so first of all, Lewis dot structure, there it is. I'm going to give it to you as Lewis dot structure. This time, though, I'm just going to go ahead and write in the other ones. Okay? So let's go ahead then, and with that said, let's take a look at the electron domains. Okay, so let's take a look at this here. We have one bond here. We have two bonds here. We have two lone pairs here. And so therefore, we have then 4 electron domains. Okay, so we have 4 electron domains in this molecule here. And of the 4, 2 are bonding, and they happen to be single bonds, and 2 are non-bonding. Sorry, what word is that? After 2 non-bonding electron domains. Okay, so there it is. 4 electron domains. That's what we have there. Okay. All right. With that said, then the 2 bonding domains are single bonds, and so therefore, I'm sorry, that was question number 2. That's 3. Okay, the Lewis dot structure is 1. Okay. Okay. So the bonding interaction then is going to be then 2 sigma bonds. So we have then 2 sigma bonds. I'm sorry, 2 sigma bonds because we have 2 single bonds. Okay, so let's go ahead and write that down. We have 2 sigma bonding interactions. Okay, so that's the bonding interaction. So with that said, then let's take a look at the electron geometry. We have 4 electron domains, and so the electron geometry here is going to be tetrahedral. This is going to be a tetrahedral geometry. And this is going to be for the electron geometry, so e.g. Okay, with that said, then, if the electron geometry takes into account all 4 electron domains, we only have 2 bonds here, and so therefore the molecular geometry here is going to be the bent geometry. Okay, that's going to be the molecular geometry for this molecule. Okay, all right. So with that said, the last question you want to be able to answer is, what is the hybridization? Okay, the hybridization around the oxygen then is going to be sp3 because we have 4 bonding electron domains. The shape is the electron geometry is tetrahedral, and so therefore oxygen is going to be sp3 hybridized, and the hydrogen again is not hybridized; it's a simple s orbital. That is going to be for the hydrogen. Okay, all right. Go ahead and save that for you. Okay. All right. Let's try another one here, folks. Let's try another one here, and let's keep working through this here. And I'm going to try to do as many as I can with you before we go on with the discussion of intermolecular forces. But let's make sure we can get this done well. Okay. So this is called carbon tetrachloride. So carbon tetrachloride, folks, same thing. Take about 2 minutes to characterize this molecule here. and then we'll go over together. Okay, so take about 2 minutes and let's get that done. Okay. Okay, let's go ahead and let's take a look at carbon tetrachloride. Okay, and first of all, let's draw the Lewis dot structure, and I'm going to go ahead and present it to you here. Okay, there's the Lewis dot structure. What I've left out of this Lewis dot structure, which I will include now, are the lone pair electrons on each of the chlorines. So let's go ahead then and let's write those in. Okay, so we have then on each of these chlorines, then we should have 3 lone pair electrons. Okay, so there it is for each one of these. So please, hopefully you include that as well. I forgot to include that in my Lewis dot structure. You always want to make sure then that you include in the lone pairs as well for obvious reasons now we know why, because these lone pairs affect the geometry of a molecule as much as the bonding pairs as well. Okay, so there it is. That's the Lewis dot structure for carbon tetrachloride. Okay, so we got the first one, the first step taken care of. Okay, let's go ahead then. Let's take a look at the next one then. Okay, we want to identify then the bonding domains around the carbon here, and let's do the same thing for the chlorine as well. The chlorines are obviously not central atoms, but we can also characterize the molecule not only in terms of the center atom, which is carbon here, but we can now also apply what we know to characterize then the chlorines as well, the atoms that are not the center atoms as well. And let's go ahead and do that together. Okay, so if you take a look at this then for the carbon atom, okay, so for the carbon atom, okay, we have then 4 electron domains total. Okay, and of those 4, we have then 4 bonding. All 4 of them are bonding domains. Okay, let's take a look at the chlorine. Okay, the chlorine then also has 4 electron domains. 4 electron domains. Okay, and for the chlorine then we have 1 bonding and 3 non-bonding electron domains. Okay, so what we're doing here is that we can characterize the molecule not only in terms of the central atom, which is what we have been doing, and that's what you should continue to do, but we can also characterize the atom in terms of the periphery atoms, the peripheral atoms, okay? The atoms that are not in the center. Okay? And we can do that because we know about electron domains, and we know how the geometries of those electron domains will situate themselves around these peripheral atoms. And based on that, we can also determine the hybridization of these peripheral atoms as well. Okay, so with that said, then let's continue on. Okay? All right, so with that, now let's go ahead then and let's characterize then the bonding interactions here. So there's only 4 single bonds here. So we only have 4 single bonds. So the bonding interactions here then is going to be sigma bonding interaction. And that's bonding interaction is not unique to a specific atom, but it's shared between 2 atoms. And so this sigma bonding interaction is used to describe both the chlorine and the carbon atom. So both the carbon and chlorine atoms will be connected together by a sigma bonding interaction. Okay? And then let's go ahead then and let's describe then and let's continue on. Okay? All right, so let's go ahead then and let's describe the electron geometry for both the carbon and the chlorine. Okay, the electron geometry for carbon then, it has 4 bonding domains. The electron geometry for carbon is going to be tetrahedral. Okay. The electron geometry for chlorine, which also has 4 electron domains, will also be tetrahedral. So both of these atoms then will be tetrahedral because they both have 4 electron domains. Again, remember, with electron geometry, we're taking into account all of the electron domains, not just the bonding and not just the non-bonding. Okay? All right, so that's for the electron geometry there. Now let's go ahead then and let's discuss then the molecular geometry. In the molecular geometry, then we are considering only the bonding domains. Okay, so for carbon has 4 bonding domains, and so therefore its molecular geometry will also be tetrahedral. Okay. But chlorine only has 1 bond. Okay, chlorine has only 1 bond. Okay, and so with only 1 bond, we know then that the geometry there will be linear. Okay, so only 1 bond, the geometry is going to be linear, and make sure you're able to do that. Okay. All right. So with that said, then the last thing I want to do then, the last thing I want to do then is describe the hybridization around each one of the atoms. I'm sorry, let me go ahead and do this side here really quickly. I'm running out of room. Sorry, but I gave myself a little bit more room here. Okay. All right. So with the hybridization, let me go ahead and let me just change color here. Okay. Hybridization for carbon first. Okay. Okay. So carbon then, and let me go. All right. Carbon then, 4 electron domains. Okay. It is tetrahedral, so we know then that carbon then will be sp3 hybridized. So this carbon here is going to be sp3 hybridized. The chlorine as well has 4 electron domains. Its electron geometry is tetrahedral, so it is also sp3 hybridized. Okay. And so in this particular case here, both atoms, the carbon and all of the chlorines, okay, both the different types of atoms, they both undergone sp3 hybridization. And that overlap here that accounts for the sigma bonding is going to be the overlap between two sp3 hybrid orbitals, and that's what gives us our sigma bonding interaction there. Okay. All right. Well, yeah. Well, I'm out of time here. So what I'm going to do tomorrow then is I'm going to do a couple more examples with you in class. If you are with me in class, then we'll work out a few more examples as well, and then I'll take your questions. But on the video lesson for tomorrow, I will go over two more. At least, I'm sorry, I'll go over at least one more example with you, and then we're going to get started into the discussion of intermolecular forces, which is the last section of this chapter. So please practice this. Please, like I said, if you can, if you're at home, you are welcome to join us with the discussion section. Just stay on with the Zoom session and then ask your questions, and I will answer your questions as well. Okay, so please make sure you understand that the discussion is not limited only to those folks who are at school. If you are at home, you can join us in Zoom as well. Okay, make sure you get your questions answered, and you can join us as I go over some extra examples, as I go over the homework as well with the folks in class. Okay, all right. Very good, folks. Have a good rest of your day, and I will see you folks either tomorrow. I'm sorry, I'll see hopefully some of you folks in person. If not, I'll see everybody tomorrow when I take a 10. Okay. All right. Have a good rest of your day, folks, and I'll see you tomorrow. Okay, bye.